Hi everybody. We're going to analyze some data together. This data is data that your physics teachers collected together to help us do some analysis and kind of think through how we would analyze the data as a model for you. All right, so what we've got here in this top part is we've got tension force and its effect on the acceleration of the cart. We changed the tension force by changing the hanging mass. Those values are listed there. We did 3 trials and we collected acceleration data 3 different times there using a motion sensor. We wanted to directly measure the acceleration and try to automate the process, take us out of the data analysis or data collection as much as possible. We didn't want to introduce error because of our reaction time or something if we had to time it. So we measured those with our motion sensor. We also did 3 trials of collecting tension force data with the force sensor. So what I've already done is I took these 3 trials of tension forces, and I average those values. 0.145 plus 0.145 plus 0.142 divided by 3 gives me 0.144. I did that for the whole column there. Same thing with acceleration. I averaged the 3 trials, and I put that over here and pipe it to that column. So I'm going to switch over to this Google Sheets spreadsheet here for the data analysis. I also brought over our constant values that might come into play a little bit later. All right, so I'm looking for a relationship between tension force, which is the unbalanced force, and the acceleration of the cart. So I'm going to select those 2. Notice I have my independent variable to the left of my dependent. That's how Google Sheets expects me to do it when I make a chart. So I'm going to insert a chart. I'm going to do a scatter plot. Put that in the sheet for us. So we get, let's label our axes here. On the x-axis, whoops, we've got our tension force. Measured in newtons. On our y-axis, we've got our acceleration. Measured in meters per second squared. And so we can understand a general relationship already. We can say as the tension force increases, so does the acceleration of the cart. That's not really a surprising result. The harder you pull on a string, the quicker the cart's going to accelerate. That is a general relationship, but we're looking for a more specific relationship. So we need to analyze the data a little more closely. Since it looks to be linear already, I'm going to go back in my advanced edit window and fit a line to it, a trend line. Scroll down to the bottom, there's a trend line, put a linear trend line in there. And I want to see the equation, so I'm going to use the equation. You see that puts it right over there in the legend. And I'm going to just stick that inside the chart just so we can see it all in one line. So that right there is the slope-intercept form of that trend line right there. All right, so now I'm going to write the mathematical model that represents our data set. So I'm going to start with this. I'm simply going to replace the y with the y values. That's acceleration. Acceleration is our y values. The slope is 1.125. I don't know the units yet. I'm going to come back to that in just a second. That's going to be pretty important to us. So I'm going to leave a spot for that. 1.125 is the slope times, let's see, the x values, those are tension forces, plus, and that's our y-intercept there, 0.017, and the units for that would be the y units, meters per second squared. So that's our mathematical model. Let me increase the size of that so you can see a little bit easier. All right, so that is the relationship based on our data between tension force and acceleration. I want to understand that a little bit better though. I don't want to say, well, the slope is 1 point, as the tension force goes up by 1, the acceleration goes up by 1.125. I want to figure out a meaning for that. Well, how can you figure out the meaning of the slope? Well, units can help you do that. So let's analyze the units here. All right, so the slope is the rise over the run. So your rise units are meters per second squared. Your run units are newtons. So the slope has units of meters per second squared over newtons. All right, so I'm going to switch over to Google Drawing here to analyze those units with you. So units for slope are meters per second squared over newtons. Well, if you look up what a newton is, it's a defined unit. A newton is equal to a kilogram times a meter per second squared. So if I replace newton right here with what it means, kilogram times meter per second squared, I get that. So this is the units for the slope of an acceleration versus force graph. And when you do that, you notice that you have something on the top and the bottom, both the numerator and denominator, that will cancel out. Meters per second squared there cancels out with meters per second squared there. So what are you left with? Well, nothing on the top, so essentially 1. And in the denominator, all you have is kilograms. So really, all of that really boils down to this. So the slope of the acceleration versus force graph is this. Newtons is replaced with what it actually means, this. And then those cancel, leaving you with a rather simple unit, 1 over kilograms. I'm going to go back here and update my mathematical model. 1 over kilograms is the unit there. Okay, so what does that slope of 1.125, 1 over kilograms, mean? Well, what does that unit make you think of? Well, if we're just kilograms, I'd think that we're a mass, but it's not. It's 1 over kilograms, so I'm thinking in my mind maybe it's 1 over mass. Well, how will I know? Well, I need to go back and check my data. All right, so based on the units of the slope alone, being 1 over kilograms, we're thinking that the slope might be 1 over the mass. We want to check that with our data to see if our data confirms that assumption or not. So let's bring up a calculator here. And let's do 1 over our mass. The mass of the cart that we're accelerating is 0.815. So 1 over the mass is that, 1.23. 1 over the mass is 1.23, 1 over kilograms. Well, that looks to be relatively close to our experimental determination of the slope. So our prediction of the slope of this graph being 1 over the mass looks like that might be correct. Now that's something valuable to know. So we're feeling pretty good about the slope being 1 over mass. Let's talk about the y-intercept real quick. The y-intercept, that looks to be very close to 0. And if I think about the situation, when the tension force is 0, the cart really shouldn't accelerate at all. So that really, if I had perfect data, would be 0. And that is very close to 0. So if I plug in 1 over mass right here, I get what is possibly a more general form of this equation. Acceleration equals 1 over mass times the force. So it's beneficial to know that's what the slope represents, because that can help me write a more general form of the equation, which can then be utilized later.